Hello, and welcome to Chapter 7, Work, Energy, and Energy Resources for Aquinas Physics Without Calculus. This is, as with all the previous lectures, going to be going over the OpenStax created PowerPoint slideshow, bouncing back and forth to the book to go over specifics and examples and expand upon ideas. This is not meant to be your only resource in the topic. It's simply meant to be one of your resources. If this helps out, fantastic. If you got questions, comment or shoot me an email, and I'll do the best I can. So, what is energy? Well, we're going to define energy in a very specific way in physics. Energy is defined. We know what energy is. Energy is the ability to do work. That's the way we define energy. It's a very specific thing. Okay. It is broad, but the phrasing of energy in the common sense is not necessarily useful for physics and for solving, say, mathematical problems. So energy is ability to do work. Well, what is work? Work, again, is specifically defined by an equation, funny enough, right? Work is defined by some force multiplied by some distance multiplied by some cosine of theta. Another way to think about that is making something move in some way. That is work. And what allows you to move something in some way is energy. When you push a lawnmower, for example, you're technically doing work. But when you're holding a briefcase, as shown in B here, you're not doing work because nothing's moving. You don't have a distance. Distance is 0. Therefore, work is 0. And there's more examples of this. Feel free to walk through this list here that's in the book to understand. But going here and moving forward, work, energy, and we get to power as well. Those are all mathematical concepts, not simply, ooh, I'm tired from all that work I did, right? Welcome to physics. Physics likes to define things in a very strict manner so that way physics can do things in a very strict manner and physics can get results, understandable, repeatable results based on its strict definitions. Mathematically, as I said before, we can actually define work as the area underneath some force over distance graph, as shown in the top section here, or honestly, the bottom section. The more you move something, the more work you're doing. So that graph B at the bottom there, each of those blue rectangles is getting larger and larger and larger, right? And if you know your calculus at all, you know what this blue rectangle is called, good for you, right? So that is the mathematical definition we're going to use for work. Energy is the stuff that allows you to work. We'll go about kinetic and potential energy later on in this video to land all these concepts, hopefully a bit more. So I said work and energy and all those things relate to one another mathematically. Let's do an example so you understand what I'm talking about here. Let's do example 7.3. I say this a lot. I'm going to say it again. When we go through questions, I do skip questions. For example, I'm skipping 7.2 for this example, which involves the same picture, funny enough. If you want, pause the video, work through 7.2 example on your own, and then come back. Please do that stuff if you need more help, okay? So, example 7.3. Determining the work to accelerate a package. Suppose that you push on the 30-kilogram package in figure 7.4, this dude here, with a constant force of 120 newtons to a distance of 0.8 meters. So you're applying a force, an F, over a distance, a D, and that the opposing frictional force averages 5 newtons. So you're pushing one direction with 120 newtons. Friction is opposing your motion with 5 newtons. And over the course of this thing, you pushed a 30-kilogram weight package 0.8 meters of a distance. Given all the information, can you calculate the net work done on the package? And can you solve that exact problem again, this time by finding the work done on each force that contributed to the net force? So what is the net work done, and what are the what is the resultant of the constant force you're applying and the frictional force opposing it? Well, we talked about work already. Work has a very specific scientific definition. It's your force times your distance times your cosine of theta. We're moving horizontally here. Okay. So if your cosine of theta is 0 degrees, what does that make cosine of theta equal to? Don't remember your circle charts and your radians and all that stuff. That's fine. Lucky for us, our calculators would do it, or we can just look at the book. If cosine of theta is 0 degrees, you're moving horizontally, the cosine of theta equals 1, which means we can essentially not care about that theta value. So what is the net work done on this? Well, we can figure out a net force, right? Because if we move 120 degrees in one direction and 5 degrees in the other, we subtract those. A net force done on this package is 115 newtons. Move distance of 0.8 meters, multiply those two together, we land at 92 joules. Joules is the SI unit of work. It comes from, a joule is a Newton meter. And since force is the unit of newtons, the unit of newtons is the unit of force, meters is the unit of distance, and theta is unitless, right? The three variables involved in work are newtons, meters, and unitless. Our end result is, of course, going to be Newton meters. We don't say Newton meters, we call it joules because it's a nicer word, essentially, right? So the package under those specific conditions has 92 joules of work in this process. Can we figure out, as I said before, what the applied and the frictional forces are actually doing in that scenario to land you at 92 joules? Well, if the total is 92 and one is in one direction, others the other direction, we must therefore have a larger total force from that 120 and a smaller negative force from the friction. It's done the exact way we're talking about here. The applied force of 120 moving in that same direction, that positive direction, gives us a 96 joule work output. But here's again the fun part of all this. What is the cosine of 180? Well, the cosine of 0 is 1. The cosine of 180 is -1. So when we apply our 5 Newton force over 0.8 meters in the opposite direction, the math is done for us by the equation to land at a -4 joule output. And again, what does negative mean at this level of mathematics? It means opposite direction. It's a directional product, not a scalar. There's no grander concept behind a number being negative other than direction. So you're pushing 96 joules in one direction and 4 joules in the other direction, and those add up to a total of 92 joules positive directionally happening. And that's the math. Again, math isn't much more difficult than we've been doing previous. In fact, I'd argue this math is a bit easier than stuff we've done previous. Most commonly, you're going to see work in terms, as I said, energy is the ability to do work. So you're going to see work and energy connected a lot. For example, we can talk about things like potential and kinetic energy. What are potential and kinetic energy? Well, potential energy is the energy imparted in something due to gravity, i.e., when you drop something, potential energy tells you what's going to happen. As you can see here from this image, the guy carrying a TV up the steps is imparting potential energy based on how high he's carrying the TV. The first story is going to bust the TV less than the second story, the third story, the fourth story if you throw it out the window, right? Funny enough, again, we're using mathematical terms here for work and energy, what have you. The person A on the outside using a lever hoist system, a pulley system to pull up the TV is probably like, you feel like you're doing less work because you're just going straight up using your arms, but the TV is still imparting the same amount of potential energy, which is according to how high it is. So TVA and TVB, when they get to their destination, H high, have the same amount of potential energy, even though arguably the guy going up the stairs is more tired. So again, let's separate out the scientific terminology from the way we use it in our day-to-day lives. Cool. Yep, as we can look at this example here, work done by the ground upon the kangaroo reduces kinetic energy to 0 as it lands. However, by applying the force to the ground on the hind legs over a longer distance, the impact of the bones is reduced. So that is referring to kinetic energy, which where are we at? I didn't show you that equation yet. Okay. Kinetic energy has its own separate equation, which is shown here in the center. Kinetic energy is energy of something when it's moving, and therefore is directly related to how fast it's moving. Kinetic energy is 1/2 mv squared. Potential energy is mgh. Mass, gravity, height is potential energy, according to gravity. And 1/2 mv squared, 1/2 times mass times the velocity squared is kinetic energy according to how fast it's moving. You can relate these things to like translational and rotational kinetic energy and like what system or what paradigm you're working in. All this stuff translates very well. But basically, the faster something's moving, or the heavier something is, or the higher it is up, the more energy it has. If it's moving, it's kinetic. If it's not moving, it's potential. Potential turns into kinetic. Kinetic results in potential. Right? They swap back and forth. The numbers, as we'll see in some math here in a little bit, always add up to equaling the same. The higher you lift something up, the faster it's falling when it hits, and the more damage it does, right? As I said previously, if you drop a TV from the first story here, it's going to do less of a bust than if you drop it from the third story because it's going to go faster because there's more potential energy to convert into kinetic energy. So let's do the classic for potential kinetic energy, the roller coaster example. Like, I guarantee you've done this exact question with probably these exact numbers in them at some point in your math career. Six. Here we go. Speed 7. What is the finding the speed of a roller coaster from its height? What's the final speed of a roller coaster shown in figure here? If it starts from rest, so not moving, right, at the top of a 20-meter hill, and work done by frictional force is negligible. We're not going to care about that for the example. Was its final speed, assuming it had an initial speed of, say, 5 meters per second. So the roller coaster example does a very good job of making sure you understand your frame of reference when you answer a question. So the roller coaster is some amount of feet above the ground, right? But the heights we care about are only in reference to what the roller coaster is capable of doing. So since the roller coaster is 25 feet above its low point, our H is 25, and everything below, like the struts and the braces of the roller coaster, that yellow part down there, I don't care about for the sake of the question, because I only care about what the roller coaster is actually going to do, right? We consider like the ground height of 0, even though the earth goes deeper, and your height above the center of the earth is irrelevant because you're not going through to the center of the earth. I hope that makes sense. Sometimes that confuses students, but you need to understand what the question is asking you in order to get the correct height. So, part A, was its final speed at the end down here? Assuming frictional forces are negligible, so I don't need to care about subtracting them out. And if you did have to care, you'd be entering like calculus territory because speed and frictional force are constantly be adjusting each other. So to find this solution, we know that the initial kinetic energy is 0. So the change in kinetic energy at the end is whatever you started at minus 0. So it's just whatever is at the end. And you can write the equation of potential energy, mgh, knowing an h, to solve out for your kinetic energy at the finish. And another fun thing about this, the roller coaster goes down into this 25-meter dip, but then it comes back up. So my question to you is, based on the friction doesn't matter, we don't have any drag from air, we have this perfect physics coaster where the wheels on the track don't matter. Do I care that the coaster goes down 25 and then comes back up 5? No, because in this perfect physics world where frictional forces are negligible, everything that's gained by going down 25, that 5 meters is lost when you come back up. So going down 25 and coming back up 5 is the same as going down 20 if I don't care about friction. In the real world, friction does matter, of course. Not going to matter here. So I can take what I have and I can solve out what I need. For example, I know my potential energy at the top of my hill up here is related to how high you are, how heavy it is, and gravity. So I am given some M, some G, and some H on the left here. And then my kinetic energy at the end is related to how heavy it is and how fast I'm going. 1/2 M V squared. So I can set these two equal to each other because all the potential energy I have when I start is converting to kinetic when I'm moving. Especially, and again, I'll also add to really nail this down. Your potential energy really only cares about height. So if you're not moving up or down, such as the end of this roller coaster, you have no change in potential energy. As soon as you move up or down, potential energy increases or decreases based on space and height change. If you go up, you're gaining potential. If you go down, you're losing potential. But when you're moving horizontally flat, you're not doing any potential energy. So we set these equal to each other. We have a mass on both sides, so I can actually cancel it. It doesn't matter how big the coaster is for this conversation. And then I'm left with gravity times height equals 1/2 V squared. Rearrange solve for V. I found that the coasters we go 19.8 meters per second. This could be a 10,000 ton coaster, or it could be a 2-ounce coaster. It doesn't matter because frictional forces are negligible. So let's take that same question, ask the final speed, assuming initial speed of 5 meters per second. So what does that mean? Well, again, we have this initial conversation of your potential energy at the start equals kinetic energy at the bottom. But in this case, since there is an initial kinetic energy, we need to care not only about the kinetic energy made by the potential, but also kinetic energy inherent in the system. Or we're not talking about just kinetic energy, we're talking about delta kinetic energy or change in kinetic energy. And what is change? Final minus initial, right? So I have an initial V naught that I have to subtract from my final V in addition to recalculating out everything else. And all that happens here is we have the exact same stuff going on. Your final is equal to your initial plus your potential. So I can rearrange and solve out what I need to solve out, right? I have an M in each section of the equation, so I can not care about math again. And I just rearrange for V and add that V naught at the end to land me at 20.4 meters per second. So even though I started going 5 meters per second, the start of all this entire process netted me a final speed addition of under a meter per second. And that's interesting, right? Just because I'm started going faster does not mean I ended going the same amount faster. Read the discussion implication section here to dig a bit deeper into this concept if you want. This potential kinetic energy conversation applies all the time to everything, right? It's kind of the fundamental way that mechanics work, that things happen. And it's super crucial to understand these concepts. Another classic potential energy conversation is a spring. You probably played with these in high school before, right? When you compress a spring, you put some sort of energy essentially into the spring by compressing it. And that energy is, as shown in this equation here in the center, is related to what the spring is made of and how far you're compressing it. K is the quantity of the spring. I think it's like something modulus. The name's in here someplace. And X is the distance you compress it. And then when you release it, the spring bounces back based on how much you pushed in. If you have a spring and you barely compress it, it doesn't give much force out. If you have a very hard spring, you compress it a lot. When you let it go, it releases a lot of energy. It's the exact same conversation as with gravity, just, I mean, it's almost the same equation even. Just instead of dealing with height, you're dealing with distance of compression, essentially. And this example also works with pulling the spring out, of course. If you pull a spring out, it snaps back. The same if you push it in and snap forward. Same conversation. And it's all about, as I've said countless times, finding your equations and doing what you need to do. What was the name of K again? I'm looking for it here. Something modulus, I want to say. Why are you not telling me, book? Whatever. Spring force. There we go. Spring force constant. What is the modulus I'm thinking of? Whatever. We'll move on. So yeah, if I ask you a question related to any amount of spring or reciprocity or shaking of something, vibrations, guitar string, for example, all does the same concept. Cool. How all this stuff works out. What is shown here in this example is kind of similar to what I was talking about before with the car, wherein if you don't take into account all those little teeny bits like drag and air force and friction and stuff like that, the math just simply cares about where you start and where you end. When this car is compressed against the spring and is let go, the math really doesn't care the path of the car. It cares about its end result. So going down the alternate path of the loop-de-loop and coming back up doesn't matter to just going straight up. All the force gained by going down is negated by going back up in a frictionless environment. So we tend to model these things in the simplest way possible because it doesn't matter. If we got friction, it does matter, and the equation becomes more difficult in the real world. But it's all the same stuff basically. Equations, here you have conservation of mechanical energy. Same thing as we talked about before with the potential energy and gravity. The amount you start with and the amount you end up with need to be the same number. If you impart 50 joules of energy into a spring, the spring's going to give you 50 joules of energy. Make sure those numbers add up at the end. Or minus PE equals KE. Same thing. Got tired. Sorry about that. This again goes over the same concept of the travel doesn't matter for the math. It's just the start and the end destinations. Similar to what we talked about before with displacement and traveling around, right? Drawing the hypotenuse between two dots to form the triangle, all that jazz we talked about in like chapter 2. It's the same base concept here. Beyond potential and kinetic energy, what else is involved there? If you have something going on, if you have a system, and we're starting to talk about real world stuff here, everything involved with the motion or the energy of a system in some way plays a part in the conversation. So here we have on the left, I think the book example is larger. There we go. Here we have on the left a spring going back and forth, bouncing a rock. Okay. So when the rock hits the spring, it compresses the spring, and the rock's potential energy turns into some mechanical spring energy, and the spring energy shoots the rock back up. But the rock does not shoot up quite as high. Why is that? Because the thing we've been skipping in all these other ones, like friction and all the other forces that exist in reality, place some sort of impact on drawing out that energy. Everything, light, sound, heat, all of these things that are produced when you do something are energy being released in a way other than movement. So when you take your hands and you rub them together and they start to feel warm, that's the friction between your hands creating heat and the energy escaping as heat. When you slap your hand on the table, the sound there is some energy being released. And the amount of energy you put into the table is not the amount of energy the table gives back to you instead of motion, because some of the energy is lost to the sound of the slap. And these are all things that you can be very particular about and find the specifics related to them, or you can just call them non-conservative forces and negate the whole concept, essentially, for the simple part of the mathematics. So we have what we're talking about here is our net work, our total work for a system, is constituted by the conservative forces, essentially potential and kinetic energies, and your non-conservative forces, everything else added together. And when you take these into account, you can describe any changes in kinetic energy based on this. And then you can further extract out how much of that is friction, how much of that is heat, light, sound, whatever, if you care about in those equations. And those can be very important, right? Certain engineering questions care a lot about heat. For example, nuclear power plants really want to know how much heat's being released from a system because they need to control that stuff so the power plant doesn't have a meltdown. Let's go over example 7.9 to expand on this a little bit. I'm going to go over 7.10 too, because it just basically is the same question, but with a theta in it. So it's good to cover that. They can confuse students sometimes. So consider the baseball player shown below. Again, way more information you need. I don't care about the color of his hat, right? But consider said baseball player as he slides to a stop on level ground. Using energy considerations, calculate the distance this 65-kilogram baseball player slides, given his initial speed of 6 meters per second, and the force of friction, the ground, fighting in his direction at 450 newtons. So what's going on here? Well, we do have some force, some velocity traveling and some mass, 65 kilograms meters per second. So he has some amount of kinetic energy. He also has some amount of non-kinetic, non-potential energy, which is the friction. The friction isn't kinetic, it's not a spring, it's not potential. So we kind of consider that the non-conservative or the other lost forces in the process. This equation right here kind of goes over what I'm talking about. Your initial kinetic plus your initial potential plus anything lost, your non-conservatives, equal your final product. So I know his initial kinetic is 1/2 mv squared, and I know his friction is pulling back from that, so it's negative. In this case, there's some force acting on it because we're given 450 newtons, so we know the force, or we know the distance being covered, and we can figure out the distance being covered. And we know that he comes to a stop at the end of this. So the friction is the force that stops him. So I need essentially to solve the question of calculate the distance. If he starts with this much kinetic energy, friction is pushing the opposite direction. How long before they equal each other? Or FD equals 1/2 mv squared, solve for D. Toss the numbers around, you end up finding he goes about 2.6 meters. So it takes 2.6 meters for this 65-kilogram baseball player moving at 6 meters per second. He slides across the dirt for 2.5 meters before he comes to a stop. That's a long time, right? That's 2.5 meters that'd be 14 feet. That's not actually what you do, right? That's a long slide in the dirt. So let's take that example and let's say he's running up a hill with a 5-degree incline, and he does what we're talking about here, the same initial speed and the same frictional force. How far do you slide when you take the incline into account? Well, we still have the exact same conversation, but now we're essentially going uphill. We're adding height. So we need to care about potential energy now. And he started at base level, so his initial potential energy down here at the start of his dive is 0. And he goes up, so he adds potential energy to himself. So when we look at our equation here, 7.62, we have an initial kinetic energy of that's a known mass velocity. We do not have initial potential energy, and we do have a non-conservative force of friction. We end up with no kinetic energy for the final because he stops moving, but we do gain potential energy because he elevated. And we have equations for all of these things. We know the work done by the non-conservative force minus FD. We know the initial. What is the final? Well, let's take a look at the equation and let's do some calculations here. So it is given to us, according to the book, by MGH turns into MGD sine theta. Why MGD sine theta? Well, Remember your SOHCAHTOA, remember? The thing I care with this triangle is this little piece here underneath the baseball player. If my angle is opposite my side, that's sine, opposite hypotenuse, right? So mgd sine theta, the d distance covered is your hypotenuse, and the sine theta refers to which side of the triangle I care about. So my potential energy is mgd sine theta. I'm still solving for my distance. I have two distances here, right? I have a distance with negative FD and I have a distance with mgd sine theta. So I need to make sure to pull things out correctly. Rearrange your equation as shown below, landing yourself at 2.31 meters. So he sliding uphill, he saved himself about a foot. Still quite a long trip for this guy to be traveling there. 6 meters per second is pretty fast, for the record. And that's what's shown in this example here. So again, hopefully you're kind of catching on here. A lot of these questions are, what's my equation? Throw it together. Think about it for a couple seconds. What's positive, what's negative, and toss everything in all nice and neat. The last parts of this conversation are conservation of energy and discussions of power. Conservation of energy is a thing I talked about a bit before. All these things need to be, you need to account for every number in the equation. The left hand of the equation, the initials, need to equal the right hand of the equations, the finals. If you add some other external force, shown here in this picture, solar power, for example, if you don't have a closed system, you need to account for all of those external energies in your end product. You never make or lose energy. You need to add up all the numbers. If you make or lose energy, you have like perpetual motion or the end of all existence. Don't do either of those things. So last topic to talk about here with a little bit of math is power. What is power? Well, power is the amount of work you do over time. We commonly call them watts, which is the SI unit equivalent to saying joules per second. So energy is the ability to do work, and power is how long it takes you to do that work. The more power you have, the more work you can get done in a faster amount of time, right? A big truck pulls a trailer faster than a small car because the big truck has more power, meaning it can exert its work at a faster rate. Either does more work, or does it in a faster time. Mathematically, you end up with the same power rating. Horsepower is a rating of power and all that jazz, but SI unit, we use the joule. This lands in a lot of things, and it's all basically taking the work equations I solve for and just dividing them by time. So do all your math for your potential and kinetics and non-conservative and other energy inputs. Divided by how long it took you to do it, that's your amount of watts it took. Another, of course, good example is batteries, right? Batteries provide a certain amount of wattage, and the more you use the battery, the faster it drains, right? Or the stronger the source, the faster it drains. That's why we use high energy LED lights as opposed to the old fluorescent ones, because those fluorescent lights would take a lot more work to produce the energy, to produce the light. Now that we have high energy, high efficiency LED lights, the flashlights and stuff, the batteries will last longer because it uses a lot less work over a larger amount of time. Let's look over question 7.2 so you can see some of this math in action. Again, the math is pretty straightforward on this. Here we have a big long list of phenomena and wattage power associated with it. Cool. A pocket calculator uses barely any energy. Fantastic. So, calculate energy costs. What's the cost of running a 0.2 kilowatt computer 6 hours per day for 30 days? The cost of electricity is $0.12 per kilowatt hour. The little K in front of the big W, kilo means 1,000, right? Kilogram, kilometer, stuff like that. So if I'm paying 12 cents per kilowatt I use every hour, and I use this computer setup, how much does it cost me? Well, since my energy is related to my power and my time, And I know that I'm using the computer 6 hours a day for 30 days. That adds up to some number, right? 6 times 3 is 6, 12, 1800, and it's 180 hours essentially. And then my power I'm spending is 0.2 kilowatts. So multiply those two guys together. I end up, this example computer is using 36 kilowatt hours. Or it was actually, 36,000 watt hours, and we just upgraded to kilowatt hours because the question asks for the answer, and the question requires kilowatts in order to get your answer out. Multiply that by 0.2, and I'm spending $4.32 a month on my computer. Notice here that the power is already given to you because that is inherently part of the conversation. The power is in watts. If I gave you stuff that gave you joules, you need to convert that over some distance. Energy is not just, work is not just motion according to classic distance, right? A computer is not moving to use energy, but the internal components are reacting and creating other forms of energy, namely heat and just the movement of the electrons and the calculations, right? So super simple math. Make sure you understand the very basic equation. Energy equals power times time, right? Or the more classic example, power equals work over time. Cool. Not too bad. Last chapter of this book goes over how this relates to humans. A lot of this last chapter is energy conservation conversations, and they are super useful, and there's like basically no math involved. So lucky us, we just get to talk about that fun stuff. Your body, of course, uses energy all the time. That's why we eat food, right? Food has energy stored in it. We call those calories. And a calorie is just another unit to describe joules. It's the unit that a dietary calorie is like 1,000. It's like 1,000 little c calories, and a little c calorie is equal to some X number of joules, some random number. But it refers like how much heat is given off when you burn a gram of something. You probably did this in chemistry class, right? Way back in high school. But the energy is basically required for our bodies to work, requires for your heart to pump blood and your lungs to inhale and exhale and all that jazz, and your brain neurons to fire. This all uses energy, sugars, stuff like that. So eat your food. Last chapter goes into world energy consumption, kind of discussing how society works. This is obviously very old here, 2006, but the world very much runs on fossil fuels, as we all know. It's a very hot button subject right now, right? Because fossil fuels, specifically oil and natural gas, are very rich in the kind of energy that powers our machines, and characteristically very easy to get the energy out. It combusts. Well, as we said before, other energy, non-conservative energy sources can include things like heat, include things like sound, and those various things. When you hear your car running, you're hearing little mini explosions of energy. Those mini explosions are turning a potential chemical energy, essentially, of the gasoline into a kinetic energy, moving your pistons up and down, driving your car and turning your tires, right? Your car works off the exact same equations we just talked about. Just instead of doing a gravitational potential energy or a spring potential energy, you have what's called a chemical potential energy. And these are like known numbers. Like the math is no different for your car than it is for these non-physics based roller coasters we've been talking about. There is, of course, a large concern about the use of energy, because most fossil fuels have a nasty byproduct called pollution. And pollution's bad, in case you were wondering. Captain Planet says so. So everyone needs to just stop polluting and the problem solved. Look at that. I just created world peace. I'm so smart. The graph at the end is kind of interesting. I'll scroll down to the big version here. And this is a graph of GDP per power consumption. Essentially, how much are we spending on the energy and how much of the energy are we using? And as you see, America is in the upper right corner. That's not the place to be. We're using a lot of energy. We're spending a lot of money to do it. Places, if you look down here to Canada, Canada uses similar amounts of energy per capita, but spends way less money, about $15,000 less. Well, probably because they have different sources of their energy, something to take into consideration. Japan, way up there in energy costs per capita. And then, other noteworthy thing, the rest of the world is way down in the bottom right corner. This is old. So this is 2007. This graph does look different today. For example, China's not in the bottom right corner. Neither is Brazil anymore. But it's still interesting to think about the energy that we're dealing with in these very simple addition, subtraction terms and the work and the power that we're talking about do have real world analogies and are vital to civilization as we know it. So understanding this, at least at a basic level, can go a long way to you understanding a lot of what's going on with society nowadays. Didn't expect that for the India physics conversation, did you? But it's kind of fun stuff. So that is my presentation. Hope you enjoyed it. Take care.